And we're recording. Hi, you all. We're excited to have you here. I want to welcome you to Flatiron School's Intro to Data Science, Teaching a Computer to Read, an Introduction to Natural Language Processing. My name is Corey Mickelson, and I am the Marketing Events Coordinator here at Flatiron School. A big part of my job is hosting free intro events like tonight's event to give you guys the opportunity to meet some of our instructors and get a better feel of the Flatiron School experience. I also host another series called Tech in 20, where we take 20 minutes to discuss hot topics within the tech industry. So a quick little reminder, we're going to be using the chat function as our main source of communication tonight. So make sure that little blue button goes from hosts and panelists to everybody so we can all chat together. And without further ado, I'd like to introduce our host for this evening, Praveen. He is one of our lead data science instructors. Go ahead and take it away, Praveen.
Sure. Hey, everyone. Thanks for joining us. I guess today will be, I don't know about, I'm sure all of you have various levels of entry points into data science, but we'll kind of be diving into natural language processing, which is one field within the broader umbrella of data science and machine learning, okay? So what is natural language processing? So natural language processing fundamentally is teaching computers, basically using computers to make inferences and predictions based off of free text, text like speech, right? I mean, think about Reddit, Facebook, all kinds of posts that have, tons of unstructured data, right? Someone saying something about someone else, right? Or, what did Elon Musk say today about, his Twitter acquisition, right? Well, maybe who cares, but whatever. But the point is that there is data in this free text that we want to be able to mine, but natural language processing natural language itself it's difficult to extract meaning, right? Or to get, from a specific set of unstructured text, get relevant data that you can use to, for example, conduct a specific task. And we'll get into what that means in a second. So there are many tasks that you can actually, with free text that you might want to do. One is a very kind of obvious one, but I mean, you have things like document classifiers, and a standard document like classification task that's often used is something like spam filtering, right? So you have a message that comes in, and then essentially you take that message, which is unstructured text, right? It's bunch of sentences, right, and words, right? And then the idea is that you have to process it in some way and then make a classification off of that. Is this email, right, based off of the words that are in the document, is this spam or is this not spam, okay? That's a very standard task. Now, in a more realistic, or where you'll often see this being deployed, besides the very standard spam, not spam, right, is things like where you have an organization, like a large organization with a lot of documents, okay? And, those documents are by and large, right? And there are many, many documents that are streaming in. People are creating tons of documents every day, right? And so the idea is that you have a large body of documents, perhaps documents that are labeled in some way, right? This particular document is about marketing, or a particular document belongs in the HR bin, or, oh, this is like about, engineering, and so on and so forth, right? And so the idea is that you take these documents that you've labeled, and what you do is you construct a classifier, some kind of classifier which trains on basically understanding the relationship between the words and the different types of documents that there are, okay? And then essentially you can use that now, right, to construct a classifier, which say you take in a new document, okay? that new document, you just have a bunch of words now, right? You don't have labels associated with it, but you can use this classifier that you've trained on the previous documents, okay, to make a determination as to what type of document that this is. Now, obviously, this is very, very useful when dealing with, document management and document management systems, okay? You can also use free text as input in something known as a regression, okay? If you're not familiar with that, that's fine. A regression is simply, in this context, is you have text reviews from, say, Yelp or something like that. And the idea is that instead of, like, for example, getting it from the ratings, what you can do is you can essentially take the free text. Okay, so there are some like ratings that are labeled in the train set. So for example, you have a review, right? Some free text. It has a rating for a restaurant. That restaurant has a rating of maybe 8. Okay, and the idea is that you basically train a machine learning algorithm, right, to sort of take the text in each review and be able to output a number for what is its probable rating number. Okay, and so in this way you can basically rate restaurants actually based on the context of the review itself as opposed to explicit stars. Okay, another thing that's often used is something called sentiment analysis, right? If a customer, right, writes a review on a product, are they like angry about the product? Are they pleased or dissatisfied, or are they happy with it, right? So, in this case, it would go from extremely, could be a scale going from extremely displeased to ecstatic, right? And this is a continuous scale, right? So, for example, 0 to 10. You're predicting, like, right, is this spam or not spam? Here, you're basically making a prediction on the number, right, or the rating, right? And so that's why this is a regression test. Okay, so moving on. By the way, if you guys don't know, this is does anyone know where this is from? Like, you can put in the chat if you do. Come on. It's from Ratatouille. It's Anton Ego, who's the famous critic, who, this is the moment where he eats the ratatouille and is reminded of his mother in France. So, he eats the ratatouille, it blows his mind. He writes some text, right? And he writes some text, and let's say that we have, trained a machine learning algorithm, right? Body of documents, okay, to essentially spit out what the rating of the restaurant probably is. Is it high or is it low, right? And if you take a look here, right, if you just even look at the words, right, you can kind of see. I mean, as you read this down, right, it's like not everyone but our great artists can come from anywhere. This is obviously a very, very, very good review. And so ideally we would want, our machine algorithm to output something really high for this. Or in the case of sentiment analysis, right, the algorithm predicts Anton is extremely pleased, okay? All right. Another task that's often employed is something known as unsupervised learning. That is that we haven't trained an algorithm here on a set of, we don't have labeled data, right? We don't have data where, okay, here was a document, it was clearly spam, and so it was labeled as spam, and we trained the algorithm to fit it as spam, right? And then another document as not spam, right? And we had a whole set of training documents. Here, it's a little different, right? The goal of unsupervised learning is actually more about uncovering structure in data. So for example, you have a collection of documents and you want to learn topics maybe what are these set of documents about, right? What type of topics are represented in these documents, okay? And if I take a particular document, can I learn what that document in terms of topics, not in terms of the words, but in terms of the topics, what topics are represented in the given document? So a picture of this, I guess, which would be helpful, right, and this is an example of a topic model, right? So you have M documents, right, just a bunch of stuff. And the idea is that, and we'll talk about this more in a little bit, but you have a cluster of basically words, right? Remember, each document has a set of words, but then the idea is that for each document, you break it down into, okay, well, this document, a particular document had some of topic one, a lot of
Apologies, it looks like we are having a technical difficulty and we will be right back.
So let me, okay, hold on one sec. Sorry about that, everyone. Okay, one sec. All right, I'm gonna share screen. Okay, all right, cool. And then, all right, so where was I? Does anybody know where I was when I stopped? Here?
I'm gonna say there. I'm gonna say close to there.
Okay.
Yes.
All right.
Evan
cool.
says yes.
Okay, good. Okay. So, all right. So in the end, so to get back to it, there are many more, types of NLP tasks besides topic modeling and classification and other things, right? And yeah, so again, we'll let's get into the meat of this, all right? So one of the main challenges in natural language processing is the need to represent information that's represented in free text in a form that's usable by a machine learning model, right? And this is actually one of the main challenges. We're going to take a very simple tack, probably the simplest way of representing information, but it turns out that actually it's rather effective for many tasks, as we'll see. This is, so the idea here is that this is a procedure known as vectorization. What it does is it effectively creates a numeric representation for the words and the documents, the documents and the words inside those documents. Okay, so let's take a very simple one, right? So as I was saying before, which is the count vectorizer. All right. Now, the count vectorizer, what it does is you have a bunch of documents. So these are the documents, these rows right here. Okay, and they're actually just simple phrases or words, right? Or I mean, like simple phrases. They're not even full documents, but nonetheless, all right? So the red dog, right? Cat eats dog, dog eats food, red cat eats. Now, the idea is that we want to represent these documents, right? By, in some way, right? Well, one way to do it is to basically take the words that are in the document and literally just count up the unique number of words, like for each unique word that appears, right? Count the number of times it appears. And in a sense, that is a representation of a document, right? It is obviously maybe not the best one that you could possibly make, but it turns out actually to be surprisingly good, as we'll see, for many, many tasks. So here, for example, the red dog, right? The happens once, right? Red happens once, dog happens once, and cat eats food doesn't appear. Now, these are all the unique words that are in the document. This, in the whole corpus or the whole set of documents, right? These words, these unique tokens or words that are in the document, in the set of documents is something known as the dictionary, and we'll get into that. So for here, for example, right, I mean, dog eats food. So here we have dog, eats, and food, right, as one, right? And then the rest are 0. Now, if I had the red cat eats red food, right, then it would be, the would be 1, right? Red would be, well, there's 2 reds because the red cat eats red food, right? So 2 reds, cat, eats, and food would all be 1, right? So this is just a way of representing the words in the document. All right. Now, the next step, is pre-processing the text, which is probably the most important part of all this, right, is really multi-step. And I'm just going to walk you through some of that. I'm not going to go into a huge amount of detail, but it's involved, okay? Here, basically, the idea is that you have a set of documents, right? And then the idea is that you have some pre-processing that goes on here, right? Tokenizing, removing stop words, lemmatizing. We'll talk about what, or stemming. We'll talk about what those are. And then this vectorizer, we're using the count vectorizer. And then once we're done with that, we'll have a term frequency matrix, which is effectively this thing that we had here, okay? Basically the terms and the frequency with which they appear in a document. And this will be a representation of our entire data set. So this is really, really essential, okay? It really helping, learning an effective, really helps, pre-processing really helps in learning a representation that's useful for making classifications or doing regression and things like that. So the first step is something known as tokenization. And literally, I mean, what it is it's essentially a way of, if you have a sentence, right? What the sentence, this is the original text in the sentence, right? And what it does is it takes the sentence and kind of uses a computer algorithm actually to chop up, the sentence into single units, right? These could be words, but they, you can see that it's also chopping the punctuation up and so on and so forth. It actually takes this word "we're" and understands that it's also a contraction, right? So we are, right? So these sorts of algorithms, so each of these single units here are tokens, are known as tokens, okay? And it's these tokens that we use actually these are the unique, essentially we use these tokens to construct the term document frequency matrix, okay? Now, the idea is that once we have these tokens, what do we do with them, right? So first of all, these rules tend to be language specific. You'll have different rules for Spanish, English, French, so on and so forth, okay? And there are different algorithms for that. In fact, it's an entire field unto itself. Computational linguists did this stuff for like 30 years before machine learning arrived. So just saying. There are many natural language processing packages with excellent tokenizers. NLTK, we're going to be using NLTK. We won't touch Spacey and Jensen, which are very advanced platforms. But the idea is, okay, we're going to go ahead and just import. This is the natural language processing toolkit, and don't worry about that. And we're going to import the command, which does what's called word tokenization. What it does is it basically takes a document and extracts all the unique tokens from it, right, for you. It tokenizes the entire thing, the entire document for you. Okay, so for example, here we have a thing called satire or no satire, right? So we want to predict whether an article is satire or whether it's real, okay? So here, all right, so we take a look at so this is the body here, it's the body of the text. And then the target here just means that, oh, it's satire. 1 means satire, 0 means not satire, right? So this is labeled text, right? The text is labeled. Now, let's take a look, right? So we knew this is satire, but is this satire or not, right? Let's just evaluate this, right? So noting that the resignation of James Mattis as Secretary of Defense marked the ouster of the top administration official, blah, blah, blah. Word populist told Reporter Friday, Jesus, we can't take back these assholes all at once, blah, blah, blah. This is just not sustainable. I'd say we can handle maybe one or more. Yeah, so the question is whether this is satire or not, right? And so the label set says this is satire. Now, what I'm going to do is I basically did the word tokenize command. Okay, so remember, this is the entire document set. And now when I word tokenized it, which is basically that chunking thing that I was talking about before, what it did was it basically chunked it, right, into all of these different elements, these unique elements, okay? You can see here, right? And it's dealt with the splitting on white space, punctuation, contractions, and so on and so forth, okay? Now, okay. Now, there are a lot of other powerful tokenizers out there, but that's not the point of this. For our use case, what we're going to do is we're going to basically, we're going to take this word tokenization, and then we want to clean it up, okay? Now, remember that when you word tokenize, right, so each token, right, we word tokenized each document in the entire collection of documents. So what we have is basically a set of tokens, right, representing, each document, okay? And now what we do is that the list of all the different token lists, so there are token lists, so you have a token list, right, for a given document, right? And then if you have an entire list of documents, a whole set of lists, then you have a list of a lot of different lists of tokens, okay? This whole thing, this list is known as the corpus, okay? It contains all of the tokens, right, that are in the body of documents, right? And the unique tokens in the entire corpus, right, the unique set across all the documents, right, is something known as the dictionary, okay? And yeah, we'll see why this is important, but I mean, we've already encountered the dictionary before. It was basically the unique, right? Like if I go back here, sorry. I go all the way back, right? For this set of documents, for example, right? This is a set of documents, right? I would have tokenized all of these, right? And then the dictionary would be the unique tokens, right? Which would just be the red dog cat eats food, okay? So that's the dictionary, right? And then the list, right? So of all of these tokens, right? If I just, the list of lists is the corpus, okay? All right, good. All right. Now, one of the main challenges of just making sense of data, right, and doing this sort of stuff in putting this stuff into machine learning is hold on, sorry. Yeah, so one of the issues, hold on, sorry, 1 second. I just went a little too far ahead. All right, I'm back to where I was. All right, so basically, for example, I mean, here's I basically am constructing the entire corpus for you, and you can see that the first, if I take a look, right, the first, down to here, right, this is a list with all the tokens that are associated with that first document, right? Then here's the next document, and so on and so forth, right? And it's all the tokens in that. And you can see that it's done, the tokenizer has done some work, right? It's, it's basically split on, it's split on contractions, like for example, here, I, apostrophe M, and so on and so forth, okay? But how is this useful to us, right? Like, well, let's just, for the process of just understanding the dictionary vocabulary, let's just take a look at this really quick, okay? So if we take a look at this, right, we can see that there is just a bunch of like, so these are all the like, these are the unique tokens, right, or the unique, the unique tokens in the entire corpus, right? So this is basically, there's 30,000 of them, okay? That's a lot. And if you take a look, I've just outputted here the tokens and basically the unique tokens in the dictionary and their count. Okay, so you can see, you have, now this is kind of interesting. So the tokens in the dictionary, in this dictionary, all 30,000 of them would become essentially columns, right, in your document, in your token frequency matrix, right? So you would have, all the tokens in here, right, and then all the documents would be over here. Okay, the list of tokens for each document, and then this would be the actual like unique tokens. All right, now in this light, let's think about the dictionary. Are there any problems? Like, look at the various types of tokens that you've seen, or is there anything that you notice? Well, the first thing is that, well, you may not know a lot about this, but 30,000 features turns out, or 30,000 unique entries that you would, it's just like, it's way too much information, it turns out, to make a prediction on accurately. And this is something in machine learning known as the curse of dimensionality. And if you come to Flatiron, we'll teach you all about it. But it makes learning very, very difficult. The other issue is that, there are many, many useless features, right? I mean, you're extracting and chunking information, right? But there's like punctuation, prepositions, or like the, articles, the, right? Like prepositions, to, on, so on and so forth, right? And in the scheme where we're throwing away a lot of context information and we're just trying to understand, like, see if we can make a prediction, right, and like capture the document, right, based just on the number of word counts, okay, like, the term frequency counts, right, then like, these sorts of things like commas, periods, like, they don't carry meaning, right? They don't carry semantic meaning, right, with which we can make predictions with, okay? These are something known as stop words, and in essence, we want to remove them. So as you can see here, right, like at the top, sure enough, right, all the stuff that really is not very useful, but also very common in the English language, right? Now, third problem, what's this? Oh yeah, I know what this is. Okay, so one issue is that it counts this word and this token as separate, right? As having separate syntactic meaning, right? It has no concept of meaning, right? But it just says, okay, these are the word and the count, right? But in essence, like we want our algorithm to learn right, in a way and make classification in a way where if the word warning appears, right, it doesn't matter whether it's uppercase or lowercase, right? I mean, that's like silly to like insist, you know. So we want to like figure out a way to clean that up and deal with that, right? Now, if you think that this is like boring, like, well, this is what, like, you know, I mean, you'll see how powerful it is. How useful it is, how important it is. It is what data scientists spend a lot of time doing. But the end result, when you do these steps properly, is like, you know, you'll just see it's like, waha, like pretty awesome, you know. But you need to take care of these things, otherwise your algorithm cannot derive like syntactic dependence and like, you know, and extract, right, like do classification effectively. For obvious reasons, as you can probably guess. Right. All right. Another one is, and it's a very, very, it's very similar in Notion, right? Is that you have warns, right? Warns appears twice, right? Warned appears 58 times. Now, warns and warned are, again, carry the same syntactic meaning, right? But they're different forms of the word. We want a way to normalize those, right? And put them into, and change the word forms so that they're the same and unified, all right? So the idea is that we want to treat all of these, since all of these features are treated as unique, right? But they're just variants of the same word, we need to normalize them in some way, just recapping. So let's get the number of tokens with only one occurrence in the entire corpus, right? That's another problem. What happens if something, if a word only appears once, right? So, sorry, about a third of the tokens only appear once, right? So, but in a sense, we're also doing kind of statistical classification. Is this spam or not spam, right? The problem is that if a word only appears once in a document that was spam, you know, you may tell your algorithm may learn, okay, when this word appears, right, which only appeared once, right? Okay, anytime this word appears, make it spam, but you don't have enough samples, right, to say, to use that word that only appeared once, right? A rare token is generally not useful, right, and can lead to erroneous results. It's not useful in building statistically robust relationships between your feature and your target, okay, which is either your class features here being you know, the tokens that you're keeping, and the target being whether it's, you know, spam or not spam, whether, you know, someone liked something or didn't like it, whatever. Okay, the final problem is that many of those tokens are numbers, and this will happen a lot, they don't have semantic meaning that will aid in classification. So let's just go ahead and just, you know, get rid of, I mean, if you take a look, right, there's a ton of these floating around, okay? So you can address these problems step by step, lower casing, removing punctuation and stop words, keeping only alphabetic tokens, and dropping numbers, okay? Now, again, with stop words, you know, right here, you can import stop words, and you have I, me, my, myself, we as like elements of stop words. And, you know, I can go through all of this, right? I mean, I'm not actually going to torture you, even though that might be, I mean, fun for me, maybe not so much fun for you. Yeah, you know, the idea here is that you go through all the lists, and you can implement this in Python, okay? You can go through this, and you can slowly clean things, right? Bit by bit, okay? Stemming and lemmatizing. This is a way of converting variants of the same word to a base root form or root. So that's one way to take care of a problem, right? So for example, change, changing, changes, changed, changer, right, goes to chang. Stem isn't always a word, but, you know, it basically stems or cuts, right? There are other similar algorithms, like, for example, sorry. Yeah, I'm not gonna. Well, here I'll run a stemmer on the document really quickly. So this is before stemming, and then this is after stemming. You can see that, like, right, some of these got chopped, right? Note, resign, right? Note, resign. Defense became defends. So on and so forth. So you can see that it's like administration became administrate. So there are some issues with stemming in the sense that, yes, it normalizes things, but it cuts things off and makes them not words. Now, that may be fine because in essence, it doesn't matter. It doesn't matter for what we're doing, but yeah. But oftentimes you do want to keep, and there are various stemmers. I'm not going to go into all the different stemmers, but you can, again, if you come to Flatiron, you can learn all about them. Advantages and disadvantages of stemming are that it's fast, right? But again, stemming is not always a word, and can produce some really weird base forms, and actually even do something very bad, which is it can merge different words together, like words that are actually different. It can chop them off, the ends off, and make them the same word, which is bad news. Lemmatization is actually often talked about, and it's something that, in essence, to convert inflections of words to a base form, not simply, cutting the root. So, for example, you can change words, is, was, will. Well, how do you cut that, right, with a stemmer? Is, was, will be kept the same as with a stemmer, but with a lemmatizer, it understands the whole word form, right? It's actually been trained to understand it. So you'll say is, was, will. Well, to be is actually the infinitive, right, of this. So it knows that, right? And it will convert is, was, will to be, right? Haves, having, had goes to have. In this case, leaves, leaves and leaves goes to leaf, right? If it's a noun, but if it's a verb, right? I mean, it might have to do something else. The important part is that, you do require some part of speech information in order to disambiguate things properly. For example, leaves, right? If it's a verb, right? It depends on whether it's a verb or a noun, right? Leaves would actually go to leave if it's a verb, right? So these are sorts of things that you don't want to mess up when you're making your algorithm. All right. Now, again, there's a lot of stuff we'll go through. We're not going to go through all of this, but in the end, what you get when you apply everything, right? I decided to apply a lemmatizer and get that all done. Is, and you can write custom functions to do all of this, right? In the end, you will get a cleaned up document, okay? A document that's completely clean with basically all of the text normalized appropriately, and you don't have, you've dropped all your infrequent tokens and things like that. Okay, now what we're going to do, since we have this satire, no satire document set, right? I'm just going to go ahead and use our term frequency matrix that we basically created by preprocessing, right? So this is this fully normalized corpus here. And I'm gonna use that, and we're actually going to put it into a very, very, very simple classifier. And see how it works, but these are the steps that you would take in pre-processing. Obviously, you can go more into depth with all of this, but let me take a look. So, all right. All right. Okay. So can everyone see this? Yeah, good. Yes, no? Okay, all right. Okay, cool. So what we're going to do now is we're going to take this term frequency matrix, like this thing that we created, right, with like all the count. Well, we're going to first, well, actually, what we're going to do is we're going to first, and what that we pre-processed and cleaned. And I didn't show you the vectorization step, but or maybe I did. Hold on. So this all is actually from the last lecture. I just put it here just so that you know what I did. And you can see here, the result of that is where we stopped off last time, okay? Sorry. Okay. Oh no. Oh no, this is going to take forever. All right. Actually, sorry about this. 1 second. Okay, you know what? We're going to switch tack. Sorry about that. That's just going to take too long. Instead of doing classification, we'll do something else. How much time do I have? Half an hour? Okay. All right. So besides classification, you can do many, many other things, right? And so one thing you can do is okay. Page down. Okay. So we've done basically up to this point, right? Where we've lemmatized and stemmed, and we want to like construct, we will construct basically a vector space representation with the counts, okay? You know, one thing that we may want is, let's say that we have a set of documents, right? You know, you can, for example, take this vector space representation and use it to classify whether emails are spam or not. But another important task is, for example, to take a set of book reviews, all right? And if you have a set of book reviews, right, maybe the book reviews were generated by a set of topics, right? They're from 3 topics, right? You know, certain words feature heavily in each topic. And so, for example, topic 1, knife, onion, parsley, chop, butter, pan, fish, okay? Well, this is clearly about cooking, okay? This topic right here, body, chop, capo, knife, caught, fishes, sleep, casino, FBI. Well, that's about the mafia, right? And then, you know, ecosystem, anchovy, catch, farming, tuna, fish, sustainable. That's about like, yeah, sustainable farming, eco stuff. Now, one thing to note is that each of these words, a lot of these words are overlapping, right? Like, right? I mean, you know, they're not mutually exclusive, but they do belong to different topics, right? And so, yeah, so that's just something to know. Now, for example, right? I mean, one example of this would be like, you know, I mean, right? Cooking with Capone, right? Goes to topic 2, right? There's probably quite a bit of topic 2, but there's also probably quite a bit of topic 1, right? So maybe we would want we want to learn to represent this book and all of its words, right? And its word document, you know, term frequency in terms of topics, right? The same thing goes for, right, with fish, right? It's a combination of topic 1 and topic 3, right? And so, right, the idea is that we take our document term frequency matrix and we want to figure out a way to represent, right, these different books in terms of their topics. Yeah, in fact, this is kind of what I have right here. Okay. Cool. I just put it in words. I mean, in numbers. All right. So one of the problems with topic modeling, right, is that you have your term document matrix, right? And you have a bunch of topics, which are, your latent topics, but you have whatever those are. In our last case, there were 3, but you don't know what word, you don't know what the distribution of words are within the topics. You just have this, but you have no idea what's in the topics, right? In addition, you have another problem, which is that if you have a topic, a document, right, you have basically a set of, topics here, okay? But you don't know what the breakdown of the topics are. So you have a double-edged problem on your hands, right? On one hand, you don't know the topics for a given document. On the other hand, you don't know the words, right, that belong within each topic. The idea here is to figure out a way to take your term document matrix and construct a representation which kind of gives you both at the same time. Now, one way to do that is to basically take your word frequency matrix, okay, and essentially factorize it, right, into two kind of subcomponents, okay. One is a word distribution for each topic, H, the weight of each topic in a given document, right? So H represents the weight of each topic in a given document. That's the second part of the problem. And W kind of represents the first part of the problem that we were talking about, right? This is just a matrix factorization. It's math, but just know that what I'm trying to do is kind of factorize this problem into 2 components. And the idea here is that I basically it's my belief that, okay, well, this was generated from, this entire thing was created by K topics, right? So the idea is that, I represent it in terms of, okay, this matrix, and this matrix. Yeah, anyway. All right. Now, yeah, we won't go through that. So what is this saying, right? I mean, let's just break it down for a quick second, right? So if I have basically my term frequencies, that's the list of numbers or the counts, right? For a given document, right? Then the idea is that I'm basically saying, okay, like, and this right here is the weight of each of the K topics, right? The idea is that I'm trying to basically construct the term frequency for a document by how much basically what the weight of each topic in a given document is, multiplied by the weights or the weight of the words for each individual topic. Okay. All right, so this is a lot. Yeah, this is way too much. All right, so, but in essence, all I'm trying to do is basically factorize how the documents are represented by both the topics that, right, the topics and the weight of the topics in each document, and then for each topic, kind of the distribution of the words that represent that topic, all right? That's in essence. I know that's like a lot, but if you, yeah, but that's in essence what it is. So for example, let's just do this for the case of COVID-19, right? Tweet analysis, right? So a think tank hires you and they want to know about trending concerns about COVID-19, right? And maybe they want higher level analytics on these concerns, distributions of concerns and issues, maybe concerns and issues that go hand in hand, and then kind of look at the issues and their importance, right, as a function of time. Maybe, for example, people care about sanitizing products, at one time, and then at another time they care about Omicron, and so on and so forth, right? And you want to be able to analyze these topics and as they appear, right, maybe as a function of time. So the idea is what I'm going to do is I'm going to take the COVID-19 tweets, a collection of them, and do some topic modeling on them real fast. And the idea or the hope is that while doing this, we construct, right, a set of topics, right, that kind of get at the heart of what each of these tweets are about, and kind of where the words that are assigned to each topic kind of make sense, right, from a human perspective, right? But we want to do this, have a computer to automatically discover this for us, okay? So I'm going to go ahead and just import what we're going to do here. This NMF, or non-negative matrix factorization, is this factorization where we did that factorizing thing, where we basically were like, okay, the words discover the word distribution within each topic, that's W, and then H is basically the distribution of topics within each document, okay? All right, and we can take a look at our data and load in our COVID-19 data set, okay? So let's go ahead and do that. All right. So we have a bunch of stuff here. There's some tweets, some text information here. So let's take a look at this. So let's take a look at some of the data. So, all right, so again, we're gonna run our pre-processing. All right, so here where we have lines at the grocery store have been unpredictable, but is eating out a safe alternative. Find out more about whether you should be avoiding restaurants right now, okay? Good. Please read this thread. Okay, that's another one. Not a particularly useful one. Want to keep your house clean, you only need to spend 5 at your supermarket, and so on and so forth, okay? Now, there are some potential cleaning tasks, and I mean, maybe you can identify some of them, but like, for example, right, you know, //r, so on and so forth. You know, there's just, you know, there's nothing here. This is basically empty information. So we want to clean that up. So we're going to go ahead and do that. Yeah. Okay. All right. Now, so basically what we're doing is we're creating our bag of words term document matrix. And we've gone ahead and actually I've created the training set for us, so we don't need to do that. But what it's done is it's basically created our account vectorized term frequency document matrix. And the idea is that, well, it can't be viewed directly, but what it does is it actually has a number of unique tokens in our term frequency matrix. Okay, so if I take a look here. It's happening again. All right, we're gonna have to wait. Sorry about that. Just give it a second. Sorry about that. All right, well, you know what? I'm just gonna go ahead and just keep going with this. Actually, yeah, I've already outputted some of this. So the idea is that, all right, we've done the topic modeling, and I'm gonna go ahead and actually fit this. So the nice thing is that scikit-learn, which is sort of a machine learning package, has a thing which can basically do this non-negative matrix factorization where it gets this W and H matrix, which encodes the importance of each token in the fitted topic, right? And H, which encodes the weight of the fitted topic of the fitted topics for each document. Okay. Now, the command for doing this is pretty simple. What I do is I take my document term frequency matrix, okay, and I just transform it, right? And when I do that, it transforms all of the documents, okay, into a topic vector representation. And we'll see what that looks like. And if I take a look at the W is actually the components. It's actually the weights for each topic, okay? Now, if we take a look, let's take a look at the tokens and columns of W with the highest weight for each topic. So this is kind of what it looks like. But if I take a look at what's in each of the topics, so I have basically weights for each word within a given topic. But let's say, so I have 5 topics here, okay? But if I take a look, right, at the topics, at the words, the most essential words that were found for each topic, let's take a look, right? Open, still, home, front, close, say. Like what it's done is the factorization has done, well, let's take a look. Amp, staff, keep, essential, work, employee, line, right? Front was somewhere over here, front. So this actual topic that has been discovered, the most prominent words that are in this collection, this topic that's been found, what do you think this has to do about? This actually has to do about frontline workers. It actually, like, the point is that by fitting and doing this factorization, this fancy math that I kind of bumbled with, to be honest, but you know, by fitting that, okay, I actually got, and under certain mathematical constraints, I was actually able to extract, okay, one topic that seems pretty coherent. Let's look at the next one. Supply, see, take, report, fall, company, gas, global crisis, oil price. Well, that's a pretty interpretable topic. That's about like oil and supply chain crisis, right? Like that, those are the top 10 words in topic 1, right? I mean, of course, again, like all the words are in each topic, but with different, all the words, all the tokens are in each topic, right? But they're in each topic with different weights, okay? That's what makes each of the topics different, okay? All right. Now, the top 10 words for topic 2 are enough, paper, help, think, toilet, please, empty, bank, stop, shelf. Well, this is about, you know, people going to the supermarket, buying things out and everything being empty, particularly, you know, toilet paper, right? We all remember that, okay? Right, so, which is just like boggles my mind that was the first thing people went for, but whatever. You know, yeah, anyway. And then here, topic 3, right? Cell, fight, virus, touch, clean, sanitizers, safe, wash, mask, sanitize. I mean, this is very clear. Okay, so clearly my lematizer didn't do what it should have done, but if it had done like, I probably would need to go back and redo that because this and this should be the same. But you can clearly see that this is about cleaning products, right? And like cleanliness, right? And sanitizing, right? And then the last thing is just about shopping, okay? Right? You've got like customer, supermarket, home, shopping, maybe delivery, right? It's just about shopping, okay? Like these are 5 very, very interpretable topics that we actually just discovered using a factorization method from the data alone. Now, one of the things that made that all possible was all the hard work that we did in the beginning. If we hadn't done all this, we would have gotten junk here. All the pre-processing and all the stuff that we did and that I talked to you about. Pre-processing is super, super important. But you can see that when you pre-process appropriately and use like a correct model, you can actually start to infer topics, okay? And have the algorithm actually discover these topics for you. it's often pretty helpful to like make visualizations about this. So don't worry about this. You know, again, right, here's the topics, right, the words. Here are all the words and their kind of weight, right, within each topic. And you can see basically what, you know, what I had up above, where I was like just showing the words, right? This is sort of a graphical representation of that. Now, we've talked about the word distributions, right? That's the W matrix that I was talking about in the slide deck. We've kind of, this all represents sort of the W matrix. That is, that this is like kind of the weight of words, of the words within each topic, right? The last step of all of this is how do we represent the document, right, in terms of topics, right? So, well, first of all, I just decided, okay, I'm just gonna label this 0, 1, 2 for like, okay, like these are just like I mean, we're just gonna label this with topic names. If I take a look, right, so far, right, the word distributions in each topic, yeah, and we basically looked at, right, looking at the topic similarity and difference, right? But, and that was all in W, but what about H? So H contains all that information, right, about breakdowns of topics in each document. And if I go ahead and take a look at that, yeah, okay. Let's take a look at some of these, okay? I'm taking specific ones as an example, right? So as the news of the region first confirmed, people flocked to area stores to purchase cleaning supplies, hand sanitizer, food, toilet paper, and other goods. Our model, right, basically learns to represent this document in terms of supply shortage and sanitizing products. Now, certainly it's about sanitizing products. It could be about supply shortage to some degree, right? If people flock to area stores, right? And you know, I think it probably learned to represent, have some degree of supply shortage because of the word flocking. Okay. Over here, right? We have, you know. All month, there hasn't been crowding in the supermarkets. However, reduced all the hours and closing the mall means everyone is now using the same entrance and dependent on the single supermarket, shopping, so on and so forth. Here's a good one. Let's see. Any impact of oil price collapse, fall in energy, blah, blah, blah. And you know what? It just clearly identifies it as like oil market crisis, right? Like, I mean, there's no question, right? Here it's, you know, can you confirm why in store signage you're not taking extra precautions in light of COVID-19? Well, what are you managed to protect your retail workers? Well, it kind of gets this wrong. That's not, you know, that just sort of happens. There's, you know, a little bit of this, but it gets the main document, the main topic absolutely correct. It's about essential workers. Okay, so this is just a sampling of the sorts of things that it's that the document term frequency matrix has been decomposed to, and the topics, right, that are learned from them. And so anyway, this is sort of, all of this is sort of representing the contents of that H matrix, right? That second matrix. In essence, if I keep going down, yeah. Now, oftentimes people will visualize some of this, like the topic space. This is something that's often done. So this may take a little bit of time, but so let it run. Sorry about that. But yeah, in essence, we found a higher level representation of the data, right? Before we started with, you know, a bunch of words, okay? And now we have a representation, like for each document, right? Just a bunch of unstructured text, right? And we basically, by structuring it, by tokenizing it, by doing all the things that we were doing, right? And by running this factorization model, we actually were able to learn, right, a new or higher level representation of the data, right, encoded in the matrix H and in the distribution of words W, right? So what's important here is that the algorithm has actually learned higher level concepts, right, that are actually useful, right, for analytics, right, and like as we were saying before, as like kind of the ultimate goal, right? And in the end, right, one part of data science, sure, is about classification, right, and constructing classifiers, right, and things like that. Another part of it is pattern recognition, right, and learning higher level representations, like basically learning for the first time, right, how to actually visualize and understand and represent data, right, generalize on it, right, in ways that are not just simply, you know, is this a cat, is this a dog, right, but, you know, something a little bit more involved than that. And that's in essence what we've done. I think at this point, I mean, this thing is still running, so this is kind of annoying. I'm actually open to I could open myself up to questions now, and then we can see where this goes, if it goes anywhere. Is that fine with you, Corey?
Oh, yeah. Does anybody have
Yeah.
any questions?
Let's take a look.
I've been looking in the chat and there was one about ways to check how these algorithms perform.
Yes, absolutely. Right. So yes, there are typically ways to check how these algorithms work. In the case of supervised learning, where you're constructing a classifier based off of training data, right? One way that can be done is essentially by, like, you know, metricizing. Okay, like you construct basically you take data that's already, like, you take aside like a test set, right, that, you know, and you basically take a look at that test set. The test set has like labels, but the idea is that you haven't fit to that data. And then the idea is that you run your classifier on the test data and you see what the classifier, your classifier predicts, right? And essentially, depending on that, right, you can figure out, you know, what the error is, classification error, and so on and so forth. So that's like a form of quality control. Usually what ends up happening is that you do this in a really automated way where you like loop through, you basically go through a whole iteration of models, like basically a set of models with different parameters. And the idea is that you look at which models are performing well, which part of parameter space is, like, for the model is not performing well, and you kind of pick based off of these metrics which one is performing the best. Now, in the case that we did, it's actually a little bit trickier because there's no labels, right? We're discovering these topics for the first time, right? So how do we know whether they're good or not? Well, my evaluation metric that I chose just now was literally looking at them and being like, yeah, they're pretty good. There are methods, and in the data science course, I do teach those methods. Basically, how in principle to use metrics to test basically what's called the coherence of the topic, right? How well the words within each topic stick together, but also how differentiated they are from the other distributions of topics, right? Like the two combined is a decent measure, but even then it's not a great measure. Unfortunately, or fortunately, whatever, unsupervised learning is a lot trickier, right? And actually does, while the metrics will help you to get to a good space or area, in the end, it's actually in the end a lot about human judgment too. Yeah. Okay. Next question. Yeah, great question. How do you decide on K? That is actually part of the tuning process for these sorts of models. So the idea is that you don't know K a priori, right? You have no idea what it is. Ideally, in many cases, you hope you have some idea, you might have some idea. In some cases, you have none, right? And in those cases, what you need to do is you need to basically, again, with this with these coherence scores I was talking about, right? Where, and certain diagnostic tools where you basically loop through, right? The number of topics that you have, right? And the idea is that the ones with the, lowest coherence score, highest coherence score in this case, right? Will be the one that you probably want to look around. Now, typically what ends up happening is that you'll get a kind of a plateau sort of. And so generally, in the coherence score, kind of like this, typically what you want to do is you want to pick the number, you want the least number of topics that describe the data, because generally the parsimonious model, Occam's razor is the best one. So you just pick the smallest one that has kind of right before the plateau hits. But yeah, anyway, yeah, deciding on K is one of the most important things. And that's where your evaluation metrics and also just you evaluating it, right? Around the kind of optimal point is that's what that's all about. And it's, very important. There are other ways to do K automatically, to derive K automatically, but they require a ton of data and they're slow. So sometimes doing it kind of this kind of manual way is a little easier. But yeah, does that answer your question? Good. All right. Oh, yeah. So here we go, right? I mean, we could take a look. Sorry. So this is this was a two-dimensional representation of all the documents. I just wanted to put this in here because, and you can see here essentially each of these points represents a document, right? And I've kind of labeled it, color-coded it by the space of, right, of kind of what the dominant topic was. And you can see here that while there is mixture, as you would expect, there is some mixture. Some documents have multiple topics. By and large, because the documents are so short, they're tweets, they're typically single topic, right? And you can see that pretty clearly here, right? They're nicely segmented. So that's just what I was going to show you. Anyway, so this all kind of makes sense. And yeah, again, to show you the H. Yeah, so here it is. So this is each of these rows are a document, and then basically these weights are sort of the document, the weight coefficient for each topic, right? So document 1 is a lot about shopping, right? And so on and so forth. So yeah, that's kind of what I want to show you. So this is that H matrix I was talking about, which was very, very abstract in the slide deck, but it's very, very, very understandable when you see it. Yeah. And anyway, yeah, that's that's it. Any other questions?
Any final questions? Okay, well, thank you again to Praveen and everyone else who joined us tonight. If you have any further questions about Flatiron School, I dropped a link to schedule a chat with our admissions team. And as a reminder, you're going to receive a copy of tonight's presentation within 3 business days after our event. And if you want to see any previous events, head to our YouTube channel and subscribe. All of that is in the chat now. Thank you all so much and have a wonderful night.
Yep. Bye. Bye, everyone. Thanks for joining us.